So, welcome back everybody to a new colloquium. It's my pleasure to introduce today's speaker, Jan Vonk from Leiden University. Jan got his PhD from Oxford. After this, he became a postdoc here at the CRM, and then he spent 1 year in the institute in Princeton before going to Leiden, where he's now a professor. And I'm happy to introduce this colloquium of today, which is called An Equation of Diophantus.
All right. Well, thank you very much for the introduction, Giovanni, and thanks so much for the invitation to speak here. Giovanni said I was a postdoc here, so it's always a great pleasure to be here and to speak to this crowd. And there's always something new still, like this room, which I had never been to somehow in all of these years. So today I wanted to talk a little bit about rational points on curves. And since it's a colloquium, I thought it would be fun to maybe keep it a little bit on the light and historical side. And one of my hopes is that for non-experts or people perhaps in different fields, it would be a little bit of an empowering experience, you know, to look at the arguments of some of the early practitioners in the area and see how they fit into how we like to think about this nowadays. Of course, looking around, I see mainly experts, so I don't know if that's going to work out, but we'll see. Maybe they're all on Zoom, exactly. Okay, exactly. All right, so I'd like to begin a while back with what is perhaps one of the first mathematical publications. Long shot, yeah. So if we can't do that, maybe someone knows already what's on this particular first paper in mathematics. I don't know if you want to help me out.
Trig table.
What's that?
It's a trig table.
Yeah, I think it's indeed, it's in essence, it is that, but it's got an arithmetic angle in that what it's listing exactly. So there's several people in the audience who know this. So I guess indeed this is the answer. I guess either you can read cuneiform, or maybe this is not your first number theory colloquium. So the Babylonians, what they did here is they tabulated, for reasons unknown to us, all of the integer solutions, or at least the first couple of integer solutions to the equation x squared plus y squared equals z squared. And so here's the first couple, which you can see also on this tablet. Now, what's interesting is that we can describe, and for being generous, we can attribute this to the Babylonians, a complete parametrization of such solutions, because all solutions need to arise from pairs of integers m comma n that are put through this map, m squared minus n squared, to mn and m squared plus n squared. And of course, for the people who were at the QVNTS yesterday, this map will look very familiar, as it played also a very important role back there. So this gives a full parametrization of all of the solutions to this particular equation. And as most of you will know, this is most easily seen in a slightly more geometric way. And so what we'll do is we'll look at a fair amount of classical arguments by early practitioners of rational points. And what I'll do is I'll give a sort of geometric interpretation, always in a little green box at the bottom of the screen. And so this green box in this particular case looks like this. I don't know if it looks green actually, but it is green. So the easiest way to see this is to say, well, okay, let's make the problem even more ambitious and not only find all integer solutions, but even all rational solutions, and postpone the problem of deciding which of those are actually integral. So by dividing out, by dehomogenizing, but dividing out by z, we reduce the problem to finding all rational points, so all rational solutions x comma y, on the unit circle, x squared plus y squared equals 1. Now on the unit circle, there's a very nice solution, minus 1 comma 0 is a nice integral point on this unit circle. And what we quickly see is that there's a bijection between all of the rational points on this unit circle and the lines through that point that have also a rational slope. And this rational slope we can write as n over m, where after some calculation one finds that the point of intersection has this particular expression. And so if we then homogenize again and worry a little bit about taking m and n integral and co-prime, we can see in this way, by not doing too much work, that we get a complete parametrization of all integer solutions in this way. So it's a very powerful geometric way of thinking about these kinds of problems that'll serve us many times to come. And it's an interesting first occurrence of this idea of proliferating solutions, starting with one solution and creating new solutions out of it through this concept of this variable line with a rational expression. On to a slightly more interesting example. This is an example that goes back to around the sorry, not the 20th century, but the 2nd century AD. And in Diophantus's Arithmetica, problem 24 of book 4 is the following. So I don't know if we have any Greek speakers in the audience. Where's Dimitris when you need him, right? Yeah. Anyway, I can tell you what the translation is in modern language. What this problem asks us to do is to take a given number n and to divide it into two numbers whose product is a cube minus its side. So that's really what the problem is. And so algebraically, what that is asking us to do is to take a number n, write it as the sum of two smaller numbers, and do that in such a way that the product of these two numbers is a cube minus that number itself, so x cubed minus x. So the equation that is there essentially on the slide, but instead of 6, you could have put any number n. That's really the problem that Diophantus asks us to solve. Now, of course, you'll say, well, that's not a very difficult problem. All we have to do is find the solution x comma y to this particular equation, and there's some obvious solutions that you can spot. Now, to Diophantus, those would not have been valid because he was really looking for rational, positive, rational solutions. He was not a big believer in this zero nonsense or this negative numbers. Any of that would not have been considered a valid solution. He really wanted a positive, rational solution. And it actually turns out to be quite difficult to find the positive, rational solution on this. And that's why this problem is quite thorny. And what he does is in the book, he explains how to solve it when n is equal to 6 by finding a rational solution to this equation. And his solution is a little bit magical. He says the following. He says, let's assume that x is equal to 3y minus 1, because why not? If we do this and we substitute, then we get 27y cubed minus 26y squared equals 0, which of course it's a cubic, but we can solve it. It's very easy. Y squared is a double root, gives us a double root of this equation. And the other solution is 26 divided by 27. And that, of course, is a valid solution for Diophantus. And that gives him the following solution. So 6 can be written as the sum of these two numbers, whose product is a cube minus, so x cubed minus x for some rational value. Okay, so it's, again, a completely algebraic solution, which is maybe a little bit mysterious as to where that particular equation comes from. Of course, Diophantus chose it in such a way that he could spot two easy solutions to the resulting cubic. And geometrically, really what he's doing is the following. So here's my little green box again. So geometrically, he says implicitly, there's an easy solution that is forbidden, which is minus 1 comma 0. And if I take the tangent line to this cubic at that point, I get precisely this equation that I had before, x equals 3y minus 1. So that's really the equation of the tangent line. And what he's doing is he's computing the third intersection point of that tangent line with this cubic again, and that's his solution to this particular problem. So I put a little picture here of this particular curve. Now, really, this construction is, of course, very significant. And again, it's an instance of a way to produce new solutions from old solutions. This method of proliferating solutions through lines that you intersect with this cubic, where you start off with some solution that you're given and you produce a new one in this way. Now, in modern language, we now understand the significance of this particular construction, and effectively it amounts to doubling a point, which is kind of interesting already historically speaking, because this is probably the first time anyone ever wrote down an elliptic curve in the literature, and immediately kind of this group law was somewhat implicit in its treatment, even though the group law took much, much longer to really formalize in the language that we have it in today. So really, you can do this construction if you're given two rational points on this cubic. You can take the line through them, take the third intersection point. And if you do this additional thing where you also reflect with respect to the horizontal axis of symmetry, that actually gives you a group law on the set of rational points. And that's what was later realized and systematically developed, even from Jacobians by Vonk. So this is what we might call the method of ascent. Going up.
Did we cover his microphone by doing this?
I'm covering the microphone? Oh, when I cross my arms. Okay, I'll try not to do that. Okay, sorry about that. Thanks. Okay. Great. So Poincaré in 1901 wrote a fantastic paper where we can see the following excerpt here on the slide. I guess I shouldn't ask if there's any French speakers in the audience. That seems like a much safer bet this time around. But this is the moment where Poincaré asks himself whether there's a way to go back. So now he's formalized this way of producing new solutions from old, this method of ascent. He's formalized that and done a completely general treatment of this on much more general objects than just elliptic curves. And so he asks, is it possible to go back the other way? Is there always some small set of fundamental solutions so that if I keep repeating this procedure, I'll hit all of the rational solutions? And he says, the number of such fundamental solutions that you need, let's call it the rank, he says. So Poincaré is really the one who coined the term here, or coined the phrase rank. It's clearly a very important invariant in the classification of rational cubics. That's what he says at the bottom. It's maybe a little bit small. I don't know if you can all see it in the back of the room, but that's what he says. Okay, so this begs the very natural question, which he already implicitly asks. By the way, it seems like he's sort of he's not really stating that there's always finitely many of these fundamental solutions, but he seems to be expecting it if you read a little bit between the lines, even though he doesn't explicitly seems to say it in this particular paragraph. What minimum amount of fundamental solutions is needed? And can you always do it with a finite set? If so, how large is that set? And that's what he calls. Okay, now this again took a while before people understood the real answer to this question. And I'll get back to that in a second, because we have to go back a little bit in time to understand and to appreciate a little bit the method by which these kinds of theorems are proved. And this is really the method of descent, so that's going the other way, which was pioneered by Fermat in this very famous instance where he solves a Diophantian equation, in this case, x to the 4 minus y to the 4 equals z squared. So he finds all the rational solutions to that. And in fact, he shows that there are no non-trivial solutions. When I say non-trivial, I mean that all of the coordinates are non-zero. So if you make one of the coordinates 0, you can spot some solutions. Other than that, there aren't any. And Fermat shows this by quite an ingenious procedure of descent, which we can have a look at. Now, it's worth noting that, of course, this is slightly stronger than Fermat's last theorem for exponent 4. It implies that, and this proof that Fermat gives of this particular equation comes after he makes his famous claim that he had an argument for all exponents. So maybe he was already aware at that time that that argument probably wasn't quite correct, given that he goes to such lengths of actually giving the proof of this particular case. Now, his method of proving this is very, very interesting. I don't know if we get any help from the audience with the Latin here. This is what a proof looked like back in those days. It's all in Latin, it's all in words also. In fact, it's amusing that this seems to be the only proof that we have of Fermat, that we have a record of at least. I'm sure he's proved lots of things, but this is the only one that we have a record of. So it's famously his only real theorem. And well, I mean, by depending on your standards, but so here it is. So here's the argument, and what we can do is we can go through it and we can translate it into modern language. And I'll put the argument. Of course, I don't have much space on this slide, so all issues of coprimality and parity I will leave to you. Yeah? So checking that things are coprime, or some things have to be even and other things have to be odd, I'll skip over that very gladly and leave that. Argument really consists of 2 steps if we break it down. And if we also maybe break it down somewhat generously, given what we know nowadays. And the first step is the following. So he says, okay, suppose we have a solution, and let's take a primitive one. So let's take a non-trivial solution so that x, y, and z have no prime factors in common, which you can always arrange by passing to a small one. If you have such a solution, you can factorize the right-hand side of this equation into x squared minus y squared and x squared plus y squared. And you can check that these 2 factors also need to be coprime. Since their product is a square, they each individually need to be a square as well. So we get that there's some s and some t that achieve this. From this s and t, you can then look at the parities. You see, s and t must be odd, both of them, you can argue. And then x and y, one of them has to be even. Let's suppose that it's y. And then out of t plus s and t minus s, one of them has to be divisible by 4. So let's assume that the stars line up in this way, and without loss of generality, we get the following factorization, which is a factorization in integers. Yeah, it's important. So we get a product of two integers, which is a square, and by the same kind of argument as before, the two are co-prime, and therefore they must each individually be a square. Let's call that u squared and v squared, and if we rearrange things slightly, we arrive at the following system of equations. So we have found an integer u and v, and they satisfy not the original equation, but this new equation, u to the 4 plus 4v to the 4 equals z squared is what they satisfy. So we started with our solution, and we produced a solution to a different Diophantin equation, u to the 4 plus 4v to the 4 equals x squared. So that's step one of the argument. Step two of the argument, which comes below on the left, is the following. You see the solution we produced, this u to the 4 plus 4v to the 4 equals x squared. This implies in particular that u squared, 2v squared, and x must be a Pythagorean triple. And this is the reason I started off with these Pythagorean triples, because, and Fermat would have been extremely aware of this, this was part of the canon of anyone practicing this field in those days. That means you can parameterize it in the way that we started today's talk with. So we can write u squared equals m squared minus n squared, etc. So using that parameterization, that goes back to the Babylonians. Okay, so we produce this m and this n that satisfy this system of equations. They can also be taken to be co-prime. Now, v squared equals mn, that's the middle equation in that system. Again, m and n are co-prime, so they must each individually be, oh, sorry, thank you. So they must each individually be squares. Let's call that a and b, their square roots. And if you go through the substitutions again, you will find that a and b satisfy the relation that a to the 4 minus b to the 4 equals u squared. That's the original equation that we started off with. So in this two-step process, we produced a new solution from this old solution. And if you check through in every step, if we started off with a non-trivial one, we actually managed to produce one whose last coordinate, that u, has become genuinely smaller in absolute value. You can trace this through. And that's, of course, quite problematic, because if we're dealing with integer solutions, that means we can keep descending ad infinitum. And Fermat argues, well, that's absurd. So this solution could only have been trivial to begin with. It's a very smart argument. And Fermat was quite proud of it, actually. He writes this in a letter also to someone else, that surely this kind of argument will have profound applications in arithmetic or something. Make some pompous sentence like that, but I think it's justified because... Yeah, maybe, exactly. Yeah, exactly. It's kind of an amusing letter to read, actually, but anyway, that's a different story. So I promised you that I was going to break down these classical arguments with my green boxes here, where I make a kind of a more geometric interpretation of what's going on. And the way we like to nowadays think of this argument of Fermat is that really to understand the solutions to this first equation, which secretly defines an elliptic curve, x to the 4 minus y to the 4 equals z squared. What he does is he uses this auxiliary second elliptic curve, the second equation, which I've labeled here by E2, which also defines an elliptic curve. And what he does is he starts with a solution here, and he makes, if it's non-trivial, a pre-image for it in that other curve under this map phi 2. And I've collected here all the variable substitutions, and I've put them there to define actual algebraic maps between these two particular curves in space. They're actually isogenies of elliptic curves if you choose the base point carefully. So he does that. He makes from this solution a solution there, a pre-image, and then he goes back in this way. Of course, assuming non-triviality. So when you have a trivial solution, that doesn't quite work. And if you unpack the arguments neatly, you can see that really what he shows is two things. So first, he shows that the rational points on E1, so E1Q, modulo the image of the rational points of E2, is actually a cyclic group of order 2. Likewise, he shows that E2Q modulo the image of phi 1 E1Q is also a cyclic group of order 2, and it's accounted for by some of these trivial solutions that you can find very easily to this equation. Now, using that descent argument from that finiteness, from that statement that they're isomorphic to Z modulo 2Z, he then argues that there's really nothing else in there, that there's no other rational points than the ones that were already accounted for. And so you find that the full list of solutions, projective solutions here, I should say, is given there. So in the first case, using this group law on the elliptic curve, you get a cyclic group of order 4. In the second case, with the second elliptic curve, you get a Klein 4 group. So, okay, we're being maybe a little bit generous here in our attribution of this to Fermat, but essentially his argument completely shows all of these claims without too much extra input. And it's a nice geometric way of viewing things. And so we see that this might be a promising way to attack this kind of problem of trying to understand the rational solutions and the group structure of these rational solutions, using perhaps this auxiliary second curve and this pair of isogenies to pass between them. Okay, and that's exactly what happened. So after Poincaré's work, there was a big breakthrough in 1922 by Louis Mordell. So Mordell wrote this paper, and it's exactly 100 years ago that he wrote this paper. So there was a conference this summer marking the 100th anniversary of this paper. Here's a little snippet of the paper. Fortunately, this time it's in English, so I don't have to ask for anyone's help. And it's kind of amusing what he says here also. He says, mathematicians have been familiar with very few questions for so long a period, with so little accomplished in the way of general results, as that of finding the rational solutions to cubic equations, essentially. I cut it off a little bit too early. It's a long paragraph, but that's what he says. And it's interesting because that's 100 years ago. And as it stands today, we haven't come that much further than his ideas, because if we try to understand really the rational points on a given elliptic curve, this is still our go-to method, and this is still really, this procedure of descent is still essentially the only tool we have of establishing these kinds of finiteness results. So it's kind of amazing that this sentiment can be echoed almost exactly 100 years later. Now, anyway, what he shows is that whenever you have an elliptic curve over Q, and you look at the group of rational points using the group law that I described earlier, then in fact, this group is a finitely generated group. It's an abelian group and it's finitely generated. And that means that it can be written as some finite abelian group T, some torsion group, direct product with a number of copies of Z. And that number of copies of Z is already what Poincaré called the rank, which so effectively it was proved by Mordell that this rank is finite. Okay, so that's quite interesting. And since we've seen a number of elliptic curves already in our historical investigations, let's see what the torsion and the rank is in those cases. So first, there's Fermat's elliptic curves, which already we kind of stated before we had the theorem here. They both have rank r equal to 0, and the torsion groups are given by these two very nice finite lines. So there's nothing new to see. It's a very interesting curve. I mean, to me, it's unbelievable that this is the first one that anyone ever wrote down. So what Diophantus, just to remind you, considers is the elliptic curve E sub n, where n is some integer in his mind. And the equation is given by y times n minus y equals x cubed minus x. Very simple equations. Let's see for a couple of values of n what the Mordell-Weil group looks like. So I computed for you the first 15 here. So already, very strikingly, there's never any torsion. No? The torsion is always trivial in these examples. And the rank is quite high. Yeah. So we see that we get rank 1 exactly once for E1, and then, oh, sorry, twice actually. E1 and E2 both have rank 1, and then we have rank 2, then 3, 2, 3, 2, 2, 3, 3, 2, 2, 3, 2. That's quite high for a family that you might randomly write down. In fact, I did let some little program run, and I gathered some statistics for all n up to, I think, about 85,000. I don't know if based on this, these 50 numbers that I've given you, you have some sort of guess that you want to make, or maybe based on, there's experts in the audience, maybe they already know what kind of percentages to check. But if you have any bets, now is the time to make them, because I'll show you the statistics in a second. But what's going to be the most common rank up to 85,000? Who thinks 1? Who thinks 2? Who thinks 3? Oh, it's a brave man. Who thinks 4? Okay. I'll tell you what happened, right? So when I computed this, I was kind of amazed. So I gave this to a master's student of mine, Bart van Kootwijk, who's currently investigating the statistics using also known heuristics that are in the literature to try and see what's going on with this family. Maybe to true experts of random statistics, this won't be a surprise at all, but for an amateur like me, this was quite surprising to see that. And you see, what's also amusing is that 3 is by far the most common, but also 4 is more common than 2, which amazes me. Yeah? So you would expect
There's something
so-
in the place of multiplicative and additive reduction. It's one of those curves that can have bias rank, or is it-
it's hard to say what happens with the reduction, because the reduction is really quite nasty as far as I can tell.
You have two parameters. It's a, you can see it as a family of elliptic curve, where n is the parameter that varies.
Sure, no, absolutely.
You know,
But
and
the generic rank,
that-
absolutely.
That's what I was aiming at.
Yeah. So certainly you get the parity equidistribution, and that's reflected in the statistics. But within the parity,
The family of elliptic curves, isn't that they should be half and half, except that there's no place, what is it? It should be no place of multiplicative reduction, or it should be, so what's a conductor?
I see. Yeah, it's hard to say. Yeah.
Where is that?
Well, okay, I don't know it. I don't know it. I can compute it. I can compute it, but it's hard to say for me right now because I don't know the expression. But it has lots of bad reduction, especially also at small primes, and I don't really know what to make of it. Anyway, it's a curiosity that I thought was quite nice, and it seems that the most brave people in the audience were actually the most correct. No one guessed 4, but that would have been a better guess than 2, apparently. We'll see. There was someone who guessed 4. Well done, whoever it was. So. Someone guessed 3, so that was quite good. It'll have generic rank. So actually, Adam Logan told us what the rank is. That's great. I can't read the full answer, but I'm sure he would know. What's that? Exactly, yeah. So the generic rank here, generic rank is 2, exactly. Exactly, yeah. That's what I thought also. So anyway, I mean, I don't want to make. That's what I was guessing also. It gets 50-50, but I don't know. I'm no expert in this. So Adam Logan says the generic rank is 2, E6 fibrate infinity, and I1. Okay, I see nodal. He means nodal singularity at the roots. I see. Very interesting. Okay, great. Yeah, thanks. Anyway, for the experts that are otherwise bored, you can think about this meanwhile, try and explain these funny statistics. It's a very nice family. Also, I mean, there was a rank 8 example in this family, and I didn't even look very far. 85,000 is that high. So who knows how high these ranks might also go up. It's kind of interesting. And I want to talk more about the torsion groups, not about the ranks, because I don't know much about the ranks. So, I don't know if I know much more about the torsion, but there's a story I want to tell you about. And we can ask, what about these torsion subgroups? What are all the possibilities that can arise for elliptic curves over Q? So, for example, we can ask, is it possible for an elliptic curve over Q to have a point of order 7? It is. It is possible. Here's an example. So here's an elliptic curve. Y squared equals x cubed minus 43x plus 166, which has the point 3, 8. It turns out to be of order 7. Now I put this mysterious orange brackets a is equal to 2 there. So I better explain to you what that means. And that's because, you see, writing down this example is almost as hard as writing down all the examples. What you could do, this is a picture, by the way, of that particular curve that I've drawn there. And this, these are all of the powers of this point 3, 8. And then there's a point at infinity of well, which makes 7. And I've also drawn some tangent lines to the points involved, and you see very nicely that they pass through the other points. So all of these gray lines are tangent lines at some point. And there's this very nice kind of combinatorial structure also that arises from this, which is related also to a classical problem called Poncelet's porism. But anyway, it's a different story. So if we want to know what all the elliptic curves are with a point of order 7, there's actually a trick that you can do to construct this example, and in fact, all of them completely. You can parameterize them by noting that, you see, whenever you have an elliptic curve E and there's a point, you have to assume also that this point is not of order 2 or 3. You can put it in the state normal form by shifting it to the origin, this point that you have, making it 0, 0, and then fiddling around a little bit with the equations by fixing some inflection point, and that will give you y squared plus uxy plus vy equals x cubed plus vx squared. So the coefficient of x squared and y is the same here. And you get these 2 variables, u and v, that you can always find such elliptic. Now, what you can do, this is just a convenient way to do the algebra, is you can express that 7 times p is equal to the identity of this group. And if you do that, I mean, you can just calculate in this curve what these multiplication equations are. In fact, it's a little bit more economical to express that 4p equals minus 3p. That gives you slightly smaller equations. If you do this in a slightly smart way, you get a relation between u and v. And this relation between u and v will allow you to completely parameterize all elliptic curves with a point of order 7. They all have that form for some a. Right? And if you want an elliptic curve defined over Q, you have to pick A to be in Q. That's a rational point. So those are the particular equations that come out. Now, this equation, this is an elliptic curve. I'm just going to remove the... This equation, it's an elliptic curve whenever the discriminant is non-zero. And if you compute the discriminant, you get this horrible looking expression, except it's not all that horrible. In fact, we kind of expect this kind of behavior. So you see that this delta, there's 3 rational values of A where it goes wrong, where it becomes singular, namely 0, 1, and infinity. There you get a singular degeneration of an elliptic curve. And then there's the 3 solutions to that cubic equation that's there. And it's a very nice cubic equation, actually. If you look at its Galois group, it's cyclic of order 3. And this the extension is only ramified at 7. In fact, it's Q zeta 7 plus, for those who know what that means. So you get these 3 degenerations of elliptic curves that are defined over this cubic Galois field, and then 3 rational degenerations also. So they add up to 6 forbidden values of A. And in the terminology that we use in the field, this means that the modular curve x17, 1 denotes here that we're looking at points of a certain order, and the 7 is the order that we're looking at. It's isomorphic to P1A. So we have a free variable. We parameterize everything in terms of this, the A line, the projective A line. And the forbidden values of A correspond to the roots of delta. These are called the cusps. So those are the singular degenerations. They don't correspond to actual elliptic curve. And we see here that we have 3 cusps that are rational and 3 cusps that are conjugate over this nice cyclic cubic field. And in general, this is true for x1 of L. Whenever you do this for another prime L than 7, you will always get this L minus 1 cusps, L minus 1 over 2 of which are rational, L minus 1 over 2 of which are conjugate over this maximal totally real subfield of Q zeta L. If that doesn't mean anything to you, that's fine. That doesn't matter all that much. But all these kind of highbrow concepts are really very simple things if you write them out. So given that I used 7 here, but maybe with a bit more pain, we could have done some different prime. Instead of 7, what about 11? What happens with elliptic curves with a point of order 11? Can we also parameterize them explicitly? Because this method seems very general. Indeed, it is quite general, but it becomes quite painful pretty quickly. And the problem is that the relations that you get between U and V, it will give you some planar curve in the UV plane, but it'll have lots of singularities, which you then have to resolve in order to find equations for the modular curve. And this gets quite tricky. Mestre has a very nice paper where he really finesses these kinds of computations. And for instance, for 11, you can do this. You can still do it by hand. And if you do this computation, you find that the elliptic curves of order, the elliptic curves with a rational point of order 11 are parameterized by a curve x111, which is given by the following equation. So no relation between the x and the y's on the elliptic curve in here. This is really the parameter space. So x and y are more like the u and v up there. It turns out that the relation is actually quite simple for the particular problem of elliptic curves with a point of order 11. It's itself an elliptic curve. It's given by this this equation y squared plus y equals x cubed minus x squared. And so if we try and solve the same problem, before we had infinitely many elliptic curves over Q with a rational point of order 7, what about 11? Well, all we have to do is find the rational solutions to this particular equation. That's kind of this thing that Mordell was doing in his proof when he proved it was finitely generated. That proof, this kind of method of descent, you can kind of make it explicit, you can make it effective, and that's what people have been doing. And certainly in the past decennia, there's been tremendous progress on doing these kinds of computations and making them effective. Now, here we have a couple of options, actually, for x111. x111, it's this equation. It's given by this equation. So you can forget that it's x111. Just look at the equation and try and solve it, some elliptic curve. We have general methods to try and do this. And the most effective, most useful one is the method of a 2 descent. Yeah? So exactly what Fermat was doing with his curves. Here it's more complicated because you see this auxiliary curve that Fermat used doesn't exist in this example. You can show it doesn't exist. This thing has no rational 2 isogenies. It has no rational points of order 2. So already to find this extra curve, you have to pass through this field extension where you adjoin the coordinates of such a 2 torsion point. That field extension, okay, it's nasty. It's a cubic field, it's maybe not so bad. The equation is there. It's alpha cubed minus alpha squared plus alpha plus 1. It's a cubic field. We have to work over the cubic field and which will boil down to some local calculations that shows the choice of 8 and 11. And following the general method, you can show that in fact, the equation has 5 solutions. And has rank 0 and has 5 solutions. Now, I'll challenge you to actually do this one. See, if you're an algebraic number theory, at least like me, you kind of grow up with this unbridled arrogance that, yeah, of course I know how to do a 2 descent. You know, you learn this when you're a master's student, and you do a couple of examples. But these things get really, really tricky. And this example, I had to do it this summer for a summer school I was doing, and I really learned a lot from actually doing it. And it's highly recommended. I mean, it'll take you an afternoon to really do it, but you learn a lot of interesting mathematics in that way. And you see that this method of 2 descent, it's really quite involved, and there's a lot of interesting things to learn. So it's quite fun to do a 2 descent on this curve. Of course, when I say do a 2 descent, it's clear that even for this simple example, you'll need a computer. It's a kind of inevitable. When you need this computer, only just to figure out the properties of this field, this cubic field, its arithmetic plays a very central role in the argument. So you have to compute its class group, you have to compute its unit group. In this case, the answers are quite nice, but already, you know, that's a bit of work. And certainly you will need a computer, I think, to really carry it out. At 2, there's something quite nasty that happens. You have to work with some totally ramified degree 3 extension of Q2 and write down elements modulo squares, and that's a little bit painful. But anyway, it can be done, and it's actually quite nice to try and do it. So it's a very effective method, and this is a general method that we have, and it follows very much these kinds of arguments that were also made by Mordell in his proof. It's very much in that spirit. It's very effective. It can be made computationally doable, and you can carry it out on lots of examples. But ultimately, we don't learn that much about the modular curve x111, because what we've done here is we've written down an equation for it and just did this general kind of very nice method, but we didn't really learn much about rational points on modular curves. We just worked with this explicit equation that was given to us. Now, if you wanted to do x1 of L for general L and figure out what possible torsion orders could arise from an elliptic curve over Q, that's a bit of a problem, right? Because even if you can write down an equation, you'll have to deal with this kind of, I don't know, it probably becomes higher genus, maybe you can work on the Jacobian. It seems kind of nasty, and if you want to do a 2 descent on that, you'll have to deal with this 2 division field, which could have any random property. So it's kind of difficult to see from this how you could get insight into rational points on modular curves or general Ls. So this is where Barry Mazur comes in. And he was really able to finesse this kind of argument and to find all the rational points on modular curves x1L in a way that teaches us a tremendous amount of information about the arithmetic of modular curves. And this is absolutely spectacular work because it achieves something really, really big, and it also teaches us something very profound about the arithmetic of modular curves. And I thought what I would do is I would illustrate maybe how I imagine Barry Mazur would have done x1 of 11. Of course, he never had to do x1 of 11 because people already knew the answer. But this is how I imagine he would have done the argument. What he would have done, I think, is to do a 5 descent on this curve by pure thought. Because already it's kind of interesting. Why do a 2 descent if there's no particularly recognizable structure happening at 2? This curve, as we already noticed, it's x111. So it has 5 rational cusps, including the cusp infinity. It has this rational subgroup of order 5. So it would always seem like a shame to not use that. There's a second auxiliary curve staring us in the face, and they're related by a pair of 5 isogenies. Of course, one good reason not to do that is that it seems completely insane to do a 5 descent, because how are you going to write down Selmer groups and elements of the Selmer group, etc. But this is where Barry Mazur had this amazing insight that if you just finesse your bounds enough, the bound gets sharp enough that you never have to write down any explicit twists of the curve whatsoever. In this particular case, it looks like the following story. So we have, again, just like in Fermat's argument, this pair of auxiliary elliptic curves. There's an x111, and then there's the image of x111 under this isogeny, where I quotient out by this rational point of order 5 that is 0, 0 on this equation. That happens to be also a modular curve. It's called x0 of 11, and its rational points parameterize elliptic curves with a rational subgroup of order 11, where the individual points may not be rational, but the group is stable under the action of Galois. Now there's a dual isogeny going in the other way, and the kernel of that dual isogeny is a mu5. So this x0 of 11 also has a point of order 5, but that's not the kernel of the dual isogeny. That goes to a different curve of conductor. So there's this pair of dual isogenies, and I've colored the kernels here in orange. Okay. Now, okay, so far I thought maybe this would be kind of somewhat empowering for people not in the field. So now just for a minute or two, I'll just address the people who know a little bit more about these algebraic techniques and give you a sketch of how this argument works. And it's very simple. You do the same descent formalism that you would normally do, but you finesse the local obstructions at 5 and 11, which are the bad primes in this particular situation. 5 is bad because it divides the degree of the isogeny, and 11 is bad because the curves have bad reduction there. But those are the only bad primes, and this is very important also in Mazur's argument. So what Mazur does is he says, when you usually do a descent, you're going to work with Galois cohomology, unramified outside of these bad primes, which is the same really as the Étale cohomology over spec of Z where you invert all of the bad primes. Now what Mazur says is, you see already at the bad prime 5, what you could do is you can refine the topology that you work with respect to. And instead of the Étale topology, you could use a flat topology, just slightly finer and better equipped to deal with group schemes of order 5 in characteristic 5, where this mu5 is really an example. If you follow the general cohomological formalism, let me talk about the top line first. So x0 of 11 and x1 of 11, they have Néron models, which are genuine abelian varieties away from 11, where the bad reduction, the toric bad reduction happens. If you take the Z1 over 11 points of that, that's the same as the Q points of the original curve. So we get this isogeny up top, whose kernel is this Z mod 5Z. The co-kernel injects into this cohomology group, which this time is taken with respect to the flat topology, of Z modulo 5Z, the group scheme Z modulo 5Z, which is also the kernel of that map over spec Z1 over 11. Requires a little argument, but by this theorem of Orton-Tate, that's the only possibility, because that's what it is in the generic fiber. Now, this flat cohomology group, well, it's the same really as the Étale cohomology group. We didn't really do anything refined at 5 here. It corresponds to, well, what are all the unramified outside of 11 extensions of Q that are cyclic of degree 5? Well, Q11 plus. Yeah, so that same field from before is the only example. And that gives you that this is really Z modulo 5Z, that whole cohomology group. So that's already enough to conclude that x0 of 11Q modulo this isogeny image of the rational points on x1 of 11 is cyclic of order 5, because we know a point on it. This point of order 5 survives in it, and that's also the upper bound, so upper and lower bounds are the same. We conclude, that's it. For the other one, you have to go slightly deeper, and there's a bit of an extra technicality, and I see that I made a mistake here. This Z1 over 11 should not be there in the second case. Otherwise, this claim that it's isomorphic to 1 is not correct. That's a bit unfortunate, because that was kind of the point I was going to try and make, but okay. So if you do the same business here, what Barry Mazur does is he finesses this argument even further by even going inside of the prime 11. You see, inside of the prime 11, now we have genuine map between Néron models, and there's a kernel of this map, which in general we can't guarantee is a finite flat group scheme. If we knew that, we would know that it was mu5, because by Orton-Tate, it's characterized by what happens in the generic fiber. Now, Barry Mazur shows that it's still mu5, even in this situation, but this is a tricky argument where he analyzes the defect, and the point of it is that the Néron model of x0 of 11 at 11 has 5 components, and 5 is divisible by 8. So very technical, fine-tuned analysis, but if you take all of that for granted, and you put a spec Z there, and you slap me on the head for forgetting to do that, so it's a flat cohomology of spec Z with coefficients in mu5. You can use Kummer theory, because the flat topology is fine enough for the Kummer exact sequence, GM goes to GM 5th power, to be surjective. So you can just use the long exact sequence in cohomology and find that this cohomology group is isomorphic to the units in Z modulo 5th powers. And the units in Z are just plus and minus 1, so that's the trivial group. So without doing any work at all, you see that the rational points on x111 modulo the rational points on x011 are just a trivial group, and that's enough. So you finesse these kinds of bounds to do a classic descent argument, modulo some technicalities in justifying that the kernels, these groups, are indeed what we claim them to be, and you get that this is indeed, oh, this is getting ahead of myself a little bit. This is indeed a curve of rank 0 and torsion group of order 5. So in a nutshell, That's what Barry Mazur would have done. Of course, in general, it's much more complicated than in this case, because, well, of course, in general, these things are not elliptic curves. So you have to work with a certain quotient of x0 of 11 that does have these properties, that has rank 0, where you can show it by these kinds of descent arguments. And Barry Mazur finds this appropriate quotient. It's called the Eisenstein quotient. And he works with this quotient to still reach the same conclusion in general. So the point is that if you had to choose between these two methods, the second one looks much more technical and much more involved. If you took the challenge, you might not object quite as much to the second method, because you see that even the first method, they shouldn't be poo-pooed. I mean, there's quite a bit of a computation happening. So maybe it's not all that much more work to make the investment to learn these techniques, because the second method is really the one that generalizes to all primes L bigger than 11. And this is precisely what Barry Mazur then pushed to the limit in order to prove a very general theorem, which I'm about to state. Now, when L is equal to 13, something strange happens. 13 is bad because, well, I guess it's not a lucky number to begin with. The reason it's bad in this case is that x0 of 30, this auxiliary modular curve that plays such a big role in the argument, has genus 0. So its Jacobian is trivial. And so that's, remember that for the future. Anyway, if we ignore this case, L equals 13, x113, by the way, Mazur had already done with Tate in a previous paper. That results in the following landmark theorem, which completely solves the problem that we set out to solve for elliptic curves over Q. It says that the only torsion subgroups that can arise in the set of rational points must be on this finite list. So Z mod 7Z is on that list. And in fact, we already showed that there's infinitely many elliptic curves with a rational point of order 7. So it should be on that list. And we have a parameterization of all of them. Z mod 11Z is not on this list. Yeah. And this we also showed, because we showed that X111 has precisely 5 rational points, but they're all cusps. Yeah. So there's no elliptic curve with a rational point of order 11. Oh, okay. Almost time to finish up. All right, so of course, once this question is completely settled, why not, look at variations of this question? You can ask for a complete classification of torsion over general number fields. So here's a paper. So this is a paper of Manin. If there's any Russian speakers in the audience, maybe no one quite wants to admit that right now, but anyway, Manin makes this kind of argument, and the theorem that he proves here at the bottom, which is stated here, is that really the order of this torsion, if you just look at the L part for some prime L, that's bounded. So the L power torsion at some prime is bounded, and it's bounded kind of uniformly in the elliptic. That's what he showed. But this bound depends on L. So, but this was kind of a first argument, which he showed using ideas for this, and then for its very short argument. Hard to actually read it. His argument, our analysis, our Galois actually results there that appeared 1 year prior to the appearance of this paper of Manin. So there's this book that Serre wrote in 1968. Whose title I forget now, but it's Elladic Representations. And do you remember the title? Exactly. An elliptic curve, fantastic. Which exactly. So this is a book that has a strong Montreal connection in that it was written here in Montreal. Now this happened in 1968, so I don't think anyone present here today was there at that time. But you were. I'm sorry. That's fantastic, though. I didn't want to presume, but I didn't want to presume that anyone was here. But you were there. That's yeah. That's quite an amazing thing to witness. You attended the. Anyway, so if you want to know more about that particular book and how that came about, you should ask Hershey. I'm sure he has some really good stories to tell about this particular book. Now, what Serre was studying in this particular book, of course, I mean, huge caricature and oversimplification, but it's really, in essence, about studying the Galois action on torsion. And so for any natural number M, we can look at the M torsion points, which over an algebraic closure always has order M squared, and there's an action of the Galois group on this thing. And if we take the inverse limit of all the automorphisms of the M torsion that we get in this way, we get the group GL2 Z hat, where Z hat is the profinite completion of Z, and a Galois representation valued in there, associated, of course, to this elliptic curve. So this is what I'll call rho sub E. Okay, so this is a theorem of Serre from 1972, which says that if we have an elliptic curve E over a number field K, And suppose that it's not special. So it's not special in this context of elliptic curves, just means that it does not have complex multiplication. So its endomorphism ring geometrically is just the ring of integers. In that case, the image of this representation has finite index. So it's an open image theorem. It's in fact an open subgroup, has finite index. So that's telling us that this kind of result that Maser shows, where it's very difficult to have a rational point of high order, is reflected in this, and that in fact, in general, if you have torsion points, they're as non-rational as can be generically, because if you act by Galois, you see that generically you expect for a prime L to get the full GL2 of FL acting on that thing, which is as big as it could possibly be. So it's a similar kind of result than what Maser showed. So as a consequence, in particular, if we just look at the action on the L torsion, then the image is maximal. I say maximal. It's the whole group really for all but finitely many primes L. And the L's that are excludable, we'll call them the exceptional primes. So a natural question we can ask is, what are all the finitely many exceptional L, which is a little bit of a generalization of what Maser showed, because of course, if you have a rational point, you're not going to have maximal image. Yeah? You always fix this line, so you're not going to have the full GL2. But in general, it could be not the whole group in several other ways. So it's kind of a generalization of this question. What are all the possible exceptional L? And at those L, what images can occur? So it's a kind of a more ambitious question where we also don't quite expect a nice answer in the same succinct form that we saw in Maser's theorem. But anyway, we can ask this question, and it's a very important question in the field. So people have thought about it a lot. And there's several ways you can interpret this question. You can try and bound how big an exceptional prime is in terms of the invariance of an elliptic curve. Now, that's one thing you can try and do. In fact, Serre conjectured, or asked, he asked a question, I guess it's not quite a conjecture, whether you can make that bound also not depend on any of the arithmetic invariance of E, whether it could be uniform completely. But that's an open problem. Now, there's various bounds that do exist that depend on the invariance of E. I mean, I'm not really an expert on these things, but I'll just mention really two. So when you have an elliptic curve over Q, such an exceptional prime must always be, it's always bounded by, let's look at this first quantity here. That's a result of, oops. Okay, I guess the laser isn't working, but the first here, the C HE to the gamma is a result of Masser and Wistholz, where HE is the Faltings height of the elliptic curve. It's the logarithm of the neural lattice of this elliptic curve. And this gamma and C are kind of absolute constants. And gamma is even effectively computable. C doesn't depend on E, and in fact, it doesn't really even depend on the number field, because what Masser and Wistholz do is really over more general number fields. The second bound looks very explicit and elementary, so it's also very nice. That's a result of Kojukaru, where she gives a bound on these exceptional primes in terms of the conductor N of the elliptic curve and the primes that divide it, which looks very explicit and appetizing like this. So there's various works that approach it in this way, trying to find such bounds on these exceptional primes. Now, you could also ask the question in a slightly different way. You could say, well, if the image of this Galois representation is not GL2 FL, then it must be contained in one of the maximal subgroups of GL2 FL. And the maximal subgroups of GL2 FL you can classify. You can make a full list of those. And for each of those types, you could try and decide whether there are any elliptic curves whose Galois image is contained in that subgroup. So it's kind of flipping the problem around. And it becomes also a geometric question, because finding all elliptic curves whose Galois images in a certain subgroup amounts to finding all of the rational points on the associated modular curve X sub H, which will depend on this choice of maximum subgroup. Now, if you take, for instance, the subgroup, which is not maximal, but you take the subgroup that has 1 on the upper left and 0 below, that corresponds to a rational point. So that's the subgroup that Maser took in his paper that I already discussed. It's contained in a Borel subgroup, which is where the 1 is not a 1, but a star, yeah, which is a maximal subgroup. And for those particular modular curves, also Barry Maser, a year later, gave a full classification of all of the rational points on the associated modular curves, which are in this case X naught of L for all L. There's also the exceptional subgroups. These things have, if you go to the projective image, there could be an A4, an S4, and an A5, and then these groups inside of GL FL sometimes that lift those. And if you contain in those, you get also a modular curve. And Serre settled all of those, except LS13. Already a bit suspicious in light of the comment that I gave earlier, but the reason is really related. So in L is 13, it's much harder. So he showed, in fact, that there's no QL points when L is bigger than 13, but L is 13 seemed to fall outside of this argument. So that's kind of missing on this list. But again, full classification with one exception. There's also the normalizers of split Cartan subgroup. So this group FL cross squared can be embedded by putting them on the diagonal, and you can look at the normalizer, which is a degree 2, so it's twice as big as this Cartan. And this, all the rational points here were solved completely in spectacular work of Bilou and Parent, which was later made effective by Bilou, Parent, and Reboledo, who showed really that all of the rational points are CM whenever L is not 13. Again, that case kind of escapes for the same reason that it would have escaped in Mazur's analysis, and the same reason that Mazur and Tate had to give a separate argument for X1. Then finally, the only remaining possibility here is a normalizer of a non-split Cartan subgroup. So FL squared star is also a subgroup of this. If you look at this normalizer, which again is twice as big, we get a modular curve, and we know essentially nothing about rational points on these modular curves. So this is completely open, and it's a very difficult, but also a very important family of curves, which I'll just make one comment on in the future. So that's kind of the status. Now, of course, you can say, well, we were doing so well, right, with X1, 11. Why don't we just write down equations for these curves and try and find all the rationals? It turns out you can actually do that. So it's not quite as systematic as what I did with the X1Ls, with this Tate normal form, etc. You have to use some tricks, but it seems that in practice, you can often just do this. So for example, in 2014, Bucco-Baran found an explicit equation for the non-split 13 case, which is also isomorphic to the split 13 case, which is the missing case in Bilou, Parent, Reboledo. So that's not coincidental that it was briefly after that, because people started really thinking about this remaining case. This is the equation that she found. Okay, so maybe your zeal is slightly diminished after you see this, because now what do, right? I mean, this is some equation, so now what? So here I've plotted this curve in the plane. This looks much more complicated. In this finite plane, there's 4 rational solutions, which I put there in a blue dot, but I don't know if you can see those. There's 3 more at infinity for a total of 7 rational points, but we didn't know how to prove that those were all the rational. Okay, so finally, in recent years, there has been more attention for a different method for attacking these kinds of problems, which does essentially that. And if the stars align, it gives you a way to find all of the rational points on certain curves, like, for instance, the curve that I have had on the previous slide. So there's this method of Chabot-Kim, Coleman also deserves some credit. So Chabot-Coleman-Kim is what I'll call it. It has a bit of flavor of a non-abelian descent. And I thought in a colloquium, I shouldn't go too far into the specifics of this method, but let me just say very briefly for people who've thought about these kinds of questions before, that the basic idea is the following. So the basic idea is to construct a family of Galois representations indexed by the rational points over QP of this curve. So you take a p-adic point, you associate to that in some analytic way a varying family of Galois representations, which will be 2G plus 2 dimensional. I made a bit of a mess here. This QP bar should be a QP. As TP should be VP, so it's the intensity with QP, but I'm sorry about that. It was a bit hasty, last minute slide adjustment. So you construct this family of Galois representations, and it varies in some interesting way, but it has a filtration where the diagonal blocks are constant. So we have these 3 representations coming just from the Tate modulo of the Jacobian. You have a QP and a QP1, but the extension class will vary in some interesting way. And this is really constructed using the fundamental group of this curve and a correspondence on it. So it only applies to curves whose Jacobians have lots of symmetries, like modular curves. So that's actually good examples for this kind of method. Once you have a Galois representation associated to these points, you can cook up natural functions on the moduli spaces of such things. The height function is the one that we use. And if you know that your point is actually a rational point, there's an additional piece of structure on this height function. There's a bilinearity of this height function that you can exploit to get a non-trivial condition and a non-trivial function that vanishes on the set of global points, the set XQ. And that's how you find this in practice. Okay, so in recent work with Balakrishnan, and Dogra, Miller, and Teitman, so a number of years we started this, and we determined the rational points on this non-split Cartan 13 curve. This was in 20 2019. This is the example I had on the previous slide. Very recently, we extended the method to be able to deal with more kinds of examples where the contributions to the height is perhaps non-trivial at other places. That was never the case for the Kerst modular curve X non-split 13, but it is for large classes of other kinds of curves. And we also settled the case of the S4 exceptional image 13, as well as all of the Atkin-Lehner quotients X0 plus L that have genus 2 or 3. There's a finite list of those, so we also solved those. So in particular, this Kerst one from 2019 and this new one, XS413, if we go back to the previous slide, settle those two remaining cases that were missing in the general classification. And at the same time, we did, as proof of concept, a couple of members of this 3 question mark family, this mysterious non-split Cartan family. And this is roughly the status, and then I'll end because I think I'm out of time. This mysterious infinite family of non-split Cartan modular curves from prime L, they're very significant. There's many reasons, but historically, they play also a big role in the proof of Hegel. The hindsight, there, how do you about it? Finding all the integral solutions on the elliptic curve X non-split 20. But in general, as Sarah pointed out, if you find the rational points on X non-split L for some L, that gives you, by similar arguments, a new proof of the class number 1 problem. Not that that's so important, but it gives a historical context for this curve. And these kinds of curves show up in lots of different contexts. So it would really be very interesting to know more about their rational points. Now, I told you we know essentially nothing, and that's really true. So let me double down on that and tell you exactly what we know, which is really not that much. The non-split L's, when L is less than 11, we do know. We know all the rational points, and this is due to the Babylonians. They found all of those curves because all these curves have genus 0, and therefore they have infinitely many rational points in these cases. So they're all completely parameterized by the methods that we saw at the start of this talk. X non-split 11 was also not so difficult because this is an elliptic curve. So you have lots of other methods to try and find the rational points, like a descent argument. So this one was settled by Ligozat in 1977, and it's an elliptic curve that has this particular equation. Its Mordell-Weil group is torsion-free and has rank 1 generated by 4, 5. Then there is the infamous Kerst modular curve, non-split 13, which I've already mentioned. We settled in 2019. It's a genus 3 curve. Its Jacobian is simple, and it has rank 3. It has precisely 7 rational points, and they're all accounted for by CM theory. Those are the CM discriminants that give you these rational points. And so what we proved is that there are no others. And then in this recent preprint, a couple of months ago, we also do the next case, non-split 70 plus, which is a genus 6 curve. The Jacobian has again rank 6. It's no longer simple. It has 3 simple factors in its decomposition, which are of dimensions 1, 2, and 3. And the ranks are also 1, 2, and 3. For sign reasons, that's what you would expect. Again, the curve has 7 rational points. They're all CM, and they're accounted for by these particular discriminants. So what's next? Well, 19, right? Of course, at some point you have to stop and think about. You can keep pushing this. The next one is genus 8, and no doubt, I mean, there's a lot of people kind of pushing this method in various ways, and no doubt this will be able to settle many more examples. But the question you have to ask at this point is also, okay, so but then what do you do? Because you're never done, right? There's always a next one to try and solve, and the G has become so big that these kinds of methods become almost prohibitively difficult to find all the rational points in them. Plus, it's not so clear that it will always work. There's still a couple of ways in which in these examples, the stars align just right, and you can really find all the rational points, but it's not so clear that really it'll keep being generalized ad infinitum, that there might be some genuine new ideas needed at some point. Of course, the elephant in the room is that we started off with x1 of 11, and we saw 2 ways of doing it. This one way, which is a general method of doing a 2 descent, which, okay, it requires some kind of computations, and it's a little bit hardcore, but people have been working on making it efficient, and it can be done, and it gives you the answers. But what about this second way? Because this is a little bit like the first way. You solve them by some general method, but you don't really learn much about rational points on modular curves in this way, because you prove that there's no other rational points because some crazy function didn't vanish on any other points. But it doesn't tell you very much about the precise rational points on modular curves, because like in the 2 descent on x111, you just work with the equation at some point and you forget that it's a modular curve completely. So that begs the question, and I think this is a very important question to ask at this point. Clearly, this is really just the beginning. And besides pushing these methods to be more generally applicable, which I think is very worthwhile, it's also worthwhile, I think, to start thinking about where's this modular approach? You know, what would Maser do in this situation? And this is not so clear at present. A very interesting recent preprint that I think takes a nice step towards this is a paper of Sachi Hashimoto. It's a recent preprint where she uses the same method, but she maybe further conceptualizes the computation of the global height by using some modular information. So by using Gros-Saguier type formulae to solve for the p-adic height in a way that really uses that this is a modular curve, that you couldn't do another curve. And I think these kinds of developments are very exciting, and I hope that in the future we'll get better insight in this avenue as well. Okay, so with that said, I hope that you'll enjoy this kind of journey going all the way back. And I hope that you see that some of these ideas that have been around for so long continue to play an underlying important role in many of these arguments. And with that said, I think I'll just thank you.
Thank you very much, Jan, for the very beautiful talk. And so now it's time for questions. We can start from the audience.
To speak in here.
You can.
So regarding this question of Serre, if you restrict to elliptic curve, let's say have a point of order 2, does the situation become simpler relative to this non-split Cartan structure?
If you add also some level structure at 2.
Yeah, so you restrict to that family, which of course is a very thin sub-collection of curves. But
yeah.
you say that the
well, I mean, I think it only increases the complexity somehow, right? Because you're adding level structure now also at 2, so the modular curve becomes bigger and higher genus, etc. But maybe the Jacobian.
These nefarious counterexamples to Chaboty, right?
What do you mean?
That the rank is equal to the dimension.
Yeah, exactly. So indeed, the Jacobian could now have these factors, which I don't know. I mean, it could be possible, but it's quite difficult. So for the particular curve, this cursed modular curve, people have tried this. And so people have been trying to look at covers and using elliptic Chaboty or all these other methods on it. But in fact, this seems to be completely impossible for this curve, this not split 13 curve. That's one of the reasons people started calling it the cursed modular curve, because that's kind of the approach where you would, you know, maybe look at coverings and try and do descent arguments there. They all seem to break down completely for these particular curves. So I don't know if this phenomenon persists beyond this particular curve, but certainly it seems that it's not always as easy as one might hope, even with this trick.
So you mentioned this problem of class number 1. So if I understand correctly, the problem translates to rational points on this 24 curve, x and s plus.
Yeah.
If I asked about CM fields of class number 1, will I be dealing with totally real points on the same curve, or it's a completely different question?
I don't know, actually. So if you take a quartic, you want to take some quartic extension and try and classify of a certain type, which ones have class number 1 with similar?
Yeah,
I don't know. I mean,
yeah, fix a real quadratic field and then look at degree.
I don't see an immediate way of doing that. I mean, the point of this argument here is usually that when you have a CM elliptic curve and the discriminant is very, very large, and this prime L is very small with respect to the discriminant, it must be inert in the CM order. And therefore, the CM point corresponding to it must give rise to a rational point. So that's usually the argument that you give. So you use CM theory and this bigness to guarantee that if there's some other one that you haven't found yet, it must actually correspond to some rational point, and therefore you find it. I don't see immediately how this kind of argument could generalize, but it's a very interesting, very interesting idea. I'm not sure.
Thank you.
Yeah, no, it's a good question.
So these examples that you have up on here, you have the rank being less than or equal to the genus. So you're in the realm in which quadratic Chaboty applies. If you go past this to like 19, 23, etc., does that continue to hold? Like, do you know, can you say anything about the rank of the Jacobian in these cases?
Yeah, so what we do know is that see this non-split plus structure at the prime L, it's exactly so that the sign will always give you that the rank is a multiple of the dimension, or at least on the simple pieces, by Gros-Saguier kind of, well, not by Gros-Saguier, but by BSD kind of argument. So this is actually also how you show that the rank is what it is in those particular cases. So the sign always lines up so that the rank is going to be equal to the genus on all of the simple pieces or some multiple of it. So it's going to have that kind of parity. So I think what could start happening after a while is that you'll start finding Jacobians maybe where the rank is generally bigger than the genus. It's a multiple of it. It's maybe 3 times the genus or something. And then it's true that the current methods wouldn't quite work. But even in those cases, you can always show, I think this is actually in the literature already, you can always show by some trace formula computations that there is always going to be a simple factor that does have rank equal to this. You can estimate precisely when this is going to happen using analytic methods. So using the signing the functional equation, you can show that actually the L value, the order of vanishing is going to be precisely 1 in those cases. And so there's always going to be some simple factor that does have rank equal to genus. It may not be the whole Jacobian that but if you're happy to work with a simple piece of it that does have this rank equal to genus, there's still good hopes that these kinds of methods will prevail. It's a little bit like what happens in Barry Mazur's argument also, that in general, of course, it's not true that J naught of L has rank 0. This is not true. There's more and more pieces, but there's always a piece that has rank 0. So if you're willing to work with a simple piece that does have rank 0, like the Eisenstein quotient, you're still good to go. And it's a similar kind of deal that you would get here, I think. If you're willing to work with a simple piece that has rank equal to genus, you're still good to go with these kinds of methods. But it's not so trivial to actually do it. Right? So in principle, it's still different from in practice. It's a great question.
Okay, if there are no more questions, let's thank Jan again for the beautiful talk.